Hello and welcome to my 8-bit TTL pipeline CPU. So I've been working on this thing for a little over a year now, and I'm pleased to say the processor core is now complete. So I've spent the last few evenings working on a piece of example demonstration code to put it through its paces a bit, which I'd like to demonstrate to you. Now, what I've implemented is an algorithm called the Sieve of Eratosthenes. He was the guy who measured the circumference of the Earth by measuring the length of shadows on the summer solstice. He's also credited with coming up with this algorithm for finding prime numbers. Right, let's give this thing a go. So it's going to skip 2 because I've used a common optimization to avoid all the even numbers, but this is basically sieving through all the primes up to 256 in the first pass, and then it's going to use an incremental variant of the algorithm to go beyond that until it's calculated all of the prime numbers within the range of a 16-bit value. So while it's doing that, I'm going to give you a quick tour around the processor. Now, this is the key component in the middle, which is the pipeline. Now, it's got 3 stages. It's got the fetch unit and the first and the second execution unit. So this allows it to have up to 3 instructions in flight at a time. Over here is the ALU. It has 2 stages to it. So pipeline stage 1 will dispatch an operation into the bottom of the ALU, and then after a cycle it will complete in the second half, where pipeline stage 2 will complete it and store the result in an appropriate register. So it's got the left and the right hand input, which handles shifting and bitwise logic, and then the second stage of the ALU can add those with a few extra bits of flag manipulation. Now, all of these various sections are configured from this diode matrix, so we've just got the 4 control lines selecting an operation that's going to be performed by the ALU. And then there's also the flag outputs back into the pipeline, so we can use it for conditional feedback. Along the bottom here is the memory subsystem. So here's memory with, at the moment, 32 kilobytes of ROM and 32 kilobytes of RAM. Here's the memory bridge, which connects the memory system to the main bus. And the main portion over here is the register stack. Now it's predominantly in 2 halves. We've got the 8-bit registers on the right, and on the left we've got the 16-bit registers. And this one along the bottom is kind of a hybrid. It's a 16-bit register which also presents itself as 2 8-bit registers, and that's how we can move data to and from the 8 and the 16-bit side. The 16-bit side is predominantly dealing with addresses. So we've got the program counter, return address, stack pointer, source index and destination index. And over here we've got the general purpose registers A, B, C and D. And we've got the constant register, which is used for loading immediates from the instruction stream. A, B, C and D can be used as either the left or the right input to the ALU, so it's pretty flexible in that regard. Now, program counter and return address, I've actually got a primitive form of register renaming that allows them to invert their operation during a function call, and so I can do call and return in a single cycle. Now, the big goal of this processor was to create a highly efficient architecture that's more akin to modern CPUs, or at least experimenting with those concepts. So I can have 3 instructions present in the pipeline at a time. The ALU operations, they can all be done back to back, so most instructions take a single cycle. The only real exceptions to that are anything that accesses memory, because that means I can't fetch an AVRA instruction because the bus is blocked. Now, that particular goal I think was highly successful. Now, one particular metric for measuring the efficiency of processors is the number of instructions you can execute per clock cycle. So comparing it to early 8-bit CPUs, the 8080, which was kind of the forerunner of the Z80 processor. Now that could do 0.145 instructions per cycle. The Z80 was the same. 6502 is a bit more efficient. It could do 0.43 instructions per cycle. But with this, running this prime numbers demonstration, it's achieving approximately 0.81 instructions per cycle, which I was very, very pleased with. So all of this was originally built on breadboard, so I've got videos for that. I'm planning next of finishing off converting the remainder of the CPU into PCBs, so I'll be doing some videos on that. But the core itself is finished. I think a lot of future time is going to be spent doing some additional peripherals. I'd like to get a proper graphical display and some sound attached to this thing, which are going to be kind of sub-projects in their own right before I call the project itself completely finished. But I think this is an outstanding milestone, and I really want to thank everyone who's been following me and providing feedback and has generally been along for the ride. If you're new to this, go ahead, hit the subscribe button if you're interested. It would be brilliant to have you along for the remainder of this journey. I very much hope you've enjoyed this. Thanks for watching. Goodbye.